Let me go over all the equations again quickly, so you will have the list of the entire thing. Now, he was saying that this equation is important, this equation is important, as if some equation is not important. Every equation is equally important. All right, so y is equal to r sine omega t. That is an equation that can tell you the position of an object in simple harmonic motion given the time. Right? And then we have velocity is equal to r omega cosine omega t. You can derive this by differentiating that equation, or I showed you the other way of resolving the components and all that and getting it the same thing. So V max is r omega. The maximum velocity in simple harmonic motion is r omega, and where does it take place? At the mean position, at the central position. Like if it is going like that, at the mean position, that's the point where the speed is supposed to be maximum, and that is this. And speed is 0 at the extreme ends. Acceleration is minus r omega square sine omega t. Remember, when I write omega t, the t and the omega are together. Okay, it's not like sine omega and then the entire thing times t. So when you're plugging this in, make sure that you put parentheses. And we have maximum acceleration is equal to r omega square. R stands for the amplitude. Yeah, slowly you have to just change over from the radius thing to the amplitude part. R stands for the amplitude, and why didn't I put the minus sign? Because I'm looking for the magnitude of the acceleration. And where's the acceleration maximum? At the extreme ends, where it turns around. That's when it is maximum acceleration.
Is R the amplitude in all those, or just the acceleration?
All of them. Yeah, we're totally into simple harmonic motion now. Why I compared it with circular motion is just for you to see how it transforms, how it is very similar at the same time, kind of different, right? It is similar in so many ways, but this is entirely a different thing because it is a to and fro motion. The other one is a circular motion that goes through plane angles, whereas this one goes through phase angles. So there's a difference in that manner. So that's the maximum acceleration equation. And you have acceleration is equal to minus omega square y. That's another equation which tells you what is the acceleration in terms of position. So if given the position, you should be able to tell this. Right, Zach?
Yes.
And then we also went through an equation which is what's the velocity at any position, which is omega square root of r square minus y squared. Did we go through that?
Yes.
Yeah. That's an equation. All of them are equally important. So, given any problem, you should be able to go and fix things. And of course, the other equations are omega is equal to 2 pi over capital T, omega is 2 pi f, and all that stuff. What is omega? What is it? Angular frequency. Right, omega is called angular frequency, not angular velocity anymore. So this is called angular frequency. So this is frequency, that's angular frequency. What's the unit of angular frequency? Radians per second. And frequency is hertz. So frequency's unit is hertz, radians per second is omega. So everything else kind of stays the same. So this is your equation. Now, I think I started off with one problem, right? The meter stick problem?
Yes.
Let's continue with that. Okay, so the meter stick is connected to the table. All right. It's tied up to the table or clamped onto the table, and the meter stick is made to go up and down. So the meter stick is made to oscillate up and down with an amplitude of 10 centimeters is what I said. I think, what was the frequency? 5 hertz. And when it is oscillating like that, up and down with a frequency of 5 hertz and an amplitude of 10 centimeters, of course the amplitude is not going to stay the same because it is going to lose energy, right?
Yeah.
And eventually it will slow down, but the frequency will stay the same. Frequency is not affected by the amplitude. Frequency is not affected by the amplitude. Frequency depends on the material of the meter stick, the length of the meter stick, and factors like that. So frequency is decided by other physical features. Okay? Amplitude depends on how much energy you put into it first. If you put in a lot of energy into it, then it will have a larger amplitude. So amplitude is purely different. Assuming that the amplitude kind of stays the same for quite some time, we should be able to do a couple of things. I think I gave you the first question as omega. What is omega? What is angular frequency? So what did you do? It is 2 pi times frequency, which is 2 pi times 5, which is 10 pi. It is always good to keep your pi as pi radians per second. It's always good to keep your pi intact because pi, if you write it as 3.14, you're chopping off a lot of places. And that can be very crucial because the timing, look at, if the frequency is this, what's the time period? 1 over 5, which is 0.2 seconds. So time period is 0.2 seconds, it's a very small time period. And I think I gave you a time, what did I give you the time?
3.673.
So add t equal to 3.673 seconds. See, look, I'm attaching a lot of precision here in the timing. And when I'm attaching a lot of this precision, it's for a reason because every oscillation is finished in 0.2 seconds. So 0.2 seconds, one oscillation is over. So these digits are very important for us in terms of timing. These are very important. If you round this timing, then it will be almost like going from here to there at the same time, right? So don't round off these timings. That's the timing given to you in 4 sig figs. So keep them as it is. So since you're keeping this as it is, if you try to round off pi in a very rough manner, that will change your answers altogether. So everyone will start getting different answers. So leave the pi as pi on your calculator itself. So at this, what was the question? Y, right? What was Y? Are you getting it? So what is the displacement at that particular time? So you just do Y is equal to R sine omega t. Well, these are the equations of simple harmonic motion. So you've done the equations for kinematics and all that. This is equations for simple harmonic motion. So you just have to use the property equation to get to your goal. So this is, now 10 centimeters must be changed to 0.1 meters. You can't like keep centimeters and all that and mix it up. So 0.1 meters sine omega 10 pi t 3.673 seconds. And if you just work it out, you get, is it a positive answer?
Yes.
A positive answer, 0.0750
meters.
So basically it is 7.5 centimeters positive. So where is it exactly? It could be somewhere there, right? So at this particular time, you're able to locate where the tip of the meter stick is. Yeah.
So for the time, we just did 1 over, what did you just do?
Time period?
Yeah.
Frequency is 1 over time period.
Okay.
Frequency is 1 over time period. You should know that. I think we've used it already. Frequency of an oscillation is 1 over reciprocal of the time period. Did we use that earlier? Never?
No.
Okay. I thought in circular motion we did. I'm pretty sure we did it. Yeah, we have used RPM and all those things. Definitely we have touched that. Yeah. We have used frequency. Just flip back, just turn your pages backward and see if you have used that equation somewhere. You have used it. Well, how do you get this from here is because we used that already.
We might not have used, we might not have called it frequency.
We did.
Oh, so we did.
I think we did. I think
Yeah, you just forgot. That's why I'm saying go back to circular motion and just look at those equations and you'll be able to find out the same stuff. Frequency. So the answer is positive 0.075 meters, which is basically 7.5 centimeters from the mean position, so which means it is right there. So we are able to locate where exactly it is. How fast is it moving at that time? At the same time, how fast is it moving? So let's find that out. How fast is it moving at that particular position? So you can find this by either this equation, because you already know the displaced position, or you can just go back and use this. So it's r omega cosine omega t, because let's use the time itself. So it's 0.1 times 10 pi times cosine 10 pi times 3.673 seconds, and you get, that'll be in meters per second, because we used everything in meters and all that stuff. You must have your calculators out. It is important, because unless you do these things, you won't get the practice of doing it. Okay, answer.
Negative.
So work this out and you get the answer of?
Negative 2.077.
Negative 2.07. So negative 2.08 meters per second. You can round it off at that point.
Mr. Sam,
Yeah.
if it hasn't, at that time, if it hasn't reached the top, how can it have a negative velocity?
It is on its way down.
Oh, okay.
Get it?
And
So this minus sign simply tells you that it has already gone up there to the top, and now it's on its way down.
Okay.
That's why you're getting a negative answer.
But I got that answer with this equation, but then I tried the v equals omega square root r squared minus y squared.
Yes, there's an issue here. You know what? When you take square root of a number, you have two options, plus and minus. And you have to take it wisely. Yeah. So yeah, this equation, you have that limitation. It could be going up, it could be coming down, we don't know. But you get the same answer, right?
I did not.
You should be getting the same answer.
Radians?
Radians shouldn't matter.
No, it doesn't matter. If you just work this out, you should get the same.
Matter.
Oh,
yeah,
if
no,
you use
no.
that, but if you use the equation for velocity.
If you can, I mean, unless you have rounded this, is it rounded? Is it fine?
No, I'm saying because you're using cosine, and if you're multiplying by pi, you have to have it in radians, otherwise it messes it up. Because I got a negative 1.35
Obviously.
whenever I use.
Yeah.
And then,
But why is
This
that?
equation?
no, the one number 3.
Yeah, it does.
Oh, so it's not negative 2.08?
It is,
It is.
but he's confused because he used the equation in number 3.
Okay.
He didn't.
No, he used this equation.
You're just you're
He used this equation. He used this 10 pi. He used this equation 10 pi root of 0.075 square. Oh no, sorry. 0.1 0.1 square minus 0.075
I
square.
didn't put parentheses with the 10 pi. Or, I don't know why. I just put parentheses around it and I got that.
That's because when you square a negative.
Yeah.
So do this first. Do this first.
Yeah, you were squaring the negative.
Yep.
Got it now?
I got it.
Okay.
Yeah.
The only confusion is when you take square root of a number like that, you have options of plus or minus, and then you have to think about it. Like you have done that in equations of motion, right?
Right.
In equations of motion, also we ended up getting v squared is this, and so what is v? Could be plus or minus, and then you decide what it is.
So how would you figure that out on this if you just knew it was there?
Well, then you have to work it out with the other equation. This equation will be definitely concrete. It will tell you exactly the answer, where it is, and how fast it's moving. What is V max
R omega.
and what is A max? Do them all. Give me the answers. What is the V max and what is the A max? V max is R omega. So just plug it in.
So it's just be a pi.
yeah.
Which is basically 3.14. Right?
Yeah.
So it's pi meters per second. And again, when you're reaching a final answer, you can always round it off to the right place. So leaving it as pi is not a problem. This is what it is. So 3.14 meters per second. What is A max? R omega square. So it's 0.1. 10 pi squared. 98.6 meters per second square. Look at the acceleration.
Should have been downward 7.
It changes according to position.
It's always because it's always to the middle.
It's always towards the middle.
Oh, yeah, you're right.
It's always towards the middle.
Wait.
So if it is up there, it is downward. If it is down here, it's upward.
Then what's the point of having the definition negative w squared?
No, this is a definition in terms of position, but for max, I don't put a minus sign. You see it?
Oh, okay.
For max, you just need the number, like at the extreme positions. This actually will tell you exactly the acceleration for a position. Like, you saw this. The velocity was negative. That means what? That means this thing is on its way down. At that position, it's on its way down. So acceleration will be directed which way? Downward. So if you want to know what is the acceleration, use this equation. Use this equation to find the acceleration at that position. The acceleration at the extreme position is this, 98.6. So the acceleration at that position should be lower. What's the acceleration right in the middle? 0. There is no acceleration here. There is no acceleration there, and acceleration is maximum 98.6 over there, 98.6 upward here, and 0 there. So it's a kind of rapid change of acceleration. Yeah.
So will the maximum acceleration always be positive?
Yeah, you can leave it as positive, just to say the magnitude. So we're not interested in the minus sign here. Maximum simply means at the extreme ends, how much is the acceleration numerically? Yes.
So why does the ruler not break? So that's 10 times the force of gravity at its max, and that's happening really quick. So like, what's stopping it from just snapping?
Because the ruler's light, so it's still not a whole lot of force.
I mean, it can hold.
The ruler is.
I mean, acceleration. Now, if I move my hands faster than 9.8, does it snap?
No.
Look at this.
Really quickly.
Look, if I drop the marker, the marker is falling with what acceleration? Okay, now I'm holding the marker in my hands. Now what happened there? Which one's acceleration is more, markers or my hands? So I'm going faster than G, right?
Right there.
So the marker is coming down with its own 9.8, but my hand went with a larger acceleration.
Right, but they can't more than 10 G's sustain kill a person.
I mean, it depends on what object you're talking about. If it is something that's made of steel and stuff like that, it should be able to. Now, again, it is not the acceleration that matters here. Pay attention. It is not the acceleration that matters here. The force is what matters. So if there's a massive object undergoing such a big acceleration, then it has to withstand a lot of force. So acceleration, yeah, smaller objects can have a larger acceleration.
Okay.
That's no big deal.
Is that why like smaller things don't break as easily? You drop them?
Like your globe.
Smaller things don't break.
Yeah. Well, so like
Oh,
if
yeah,
you take
yeah.
a smaller shark.
Yeah, you can think about it that way, yes.
If you take it.
When it bounces somewhere, it actually, is suffering a lot of acceleration, but since the mass is small, then it can withstand that force. That's basically. Alright, so you got this, so you should be able to use this equation freely to find out whatever you want. Do you understand that clearly? Alright, how fast is it moving when the displacement is minus 0.05 meters? How fast is it moving when it is negative 0.05 meters? How fast is it moving? So which equation is going to be useful there? How fast is it going to move? How fast is it moving? So
V equals
what is V at y equal to negative 0.05 meters? So you have to use this equation because that's the equation that connects you to. Yes. So V is equal to omega square root of r square minus y square 10 pi square root of r square, which is 0.1 square minus Now since it's getting squared, the minus sign sitting here doesn't make a difference. So even if you don't put a minus sign inside this bracket, it is fine, right?
Yeah.
Because the minus square is again positive. So by chance, if you forgot to put the minus sign, no big deal. Yeah, so what's the answer for that? So you get an answer of plus or minus what?
I got 2.7.
2.7.
3.14 is the highest speed, so it can't be higher than that.
2.7.
Yeah.
2.7.
2.7 meters per second. Exactly.
2.720.
2.72 meters per second. Plus or minus. That means no.
No, it's minus.
No, I can't say.
Oh yeah. Wait.
We don't know which way it's going.
You don't know which way it's going. So the answer is plus or minus 2.72 meters per second. Pay attention to all these details. Very, very important. When you get an answer of plus or minus 2.72 meters per second, you know the position is here, but you don't know whether it is on its way that way or on its way that way. You don't know that. And therefore, both answers are probably correct. But again, finer details given to you will tell you exactly what's happening.
So it's not even possible to figure out.
No. Just by this information, no way. Because you only know the position.
Wait.
That way you cannot tell.
No.
Yeah, you cannot tell. Just by position you cannot tell. Because you have plus or minus options. So it could be on its way downward. It could be on its way upward. Both possibilities are there. So you cannot just decide on this. Alright, any questions on this? Clear? You will see multiple situations where you end up using these equations. These are the simple harmonic motion equations, and you should be able to freely use this. Now, what is the acceleration at this point? What is the acceleration at that point?
It's cake. It's
What is the acceleration at that same position? So use this equation. At that position. So acceleration is equal to minus omega square y. So minus 10 pi square.
49.3.
And y is negative 0.05. And what do you get?
49.3.
A positive answer?
Yep.
Positive what? 49.3? So 49.4? Is that right?
Close enough.
Yep.
49, and you're getting a positive answer here. What does that mean?
It means the acceleration is towards the center.
That's it. Acceleration is that way, towards the main position, and that is upward. So even though you don't know which way it's going, acceleration is always that way. So the acceleration is always directed to the mean position, whichever way it's moving. You understand that? So whether it is on its way up or down, the acceleration is still that way. Whether it's below at any level, whether it's going below, this way or that way, still the acceleration is true. So acceleration is always towards the mean position. That is a very important point on the statement for simple harmonic motion definition. Acceleration is directly proportional. So this is your simple harmonic motion's definition. Acceleration is directly proportional to the displacement from the mean position, and acceleration is directed to the mean position. The minus sign tells you that. Okay? So when the displacement is positive, acceleration is downward. When the displacement is negative, acceleration is upward. Positive. All right. Now let's look at some of the some situations where you have simple harmonic motion. So, is this simple harmonic?
No.
No? Why?
Not
I mean,
period.
well, it would be if it was an elastic collision.
And if it didn't go back to where it started.
Why is this not simple harmonic?
Not periodic, not going back. It's not.
Isn't
the
it?
accel- the
Isn't it to and fro?
The acceleration is not always towards the center.
The acceleration is not always towards the center because if you look at the center, mean is here.
Yeah.
Acceleration is always downward until
Yeah.
it touches the table, right?
Yeah.
What's the acceleration?
Negative, not one.
And according to your equation, a is equal to minus omega square y, it tells you that acceleration depends on the position, right? So that doesn't work at all. So in this case, absolutely, this is not simple harmonic. So how do you decide if a motion is simple harmonic? Is by just looking and checking whether those conditions are satisfied. Which conditions? Acceleration should be directly proportional to the displacement, and acceleration is directed to the mean position. These two things. Yeah.
So would a metronome be an example of simple harmonic motion?
Yeah, that's an oscillation.
Oh, yes.
Yeah. That's an oscillation.
Yeah.
But that is actually powered, you know. It's not a free oscillation. If something is free oscillation, that is simple harmonic. No, that is simple harmonic. That is we're going to talk about this right now. So that is simple harmonic. The simple pendulum. We're going to do an experiment on pendulum, which is also going to be simple. So simple harmonic motion is a to and from motion where the acceleration is directly proportional to displacement and it is directed towards the mean position. That's why we have that minus omega squared y. Okay? Now let's look at some of the stuff that is simple harmonic. And you'll see how it's connected and how you can get information from there. How you can get information from there. Let's take the Earth. All right? Now, what's the diameter of the Earth? How much?
At least 11.
What 11?
11.
Miles?
At least 11.
I have no idea.
11.
At a bare minimum 11.
That means if you kind of make create a well and go all the way, how deep you should go to reach the center of the Earth? That is
Let's say
radius.
5 miles.
800,000. The diameter of Earth, it says that it is 7,917.5 miles.
The radius is approximately 4,000 miles.
Whoa.
Yeah, you don't think that you're sitting on a small
That's deep.
sphere.
That's a lot of miles.
Yeah, it is 4,000 miles from here to here. And another 4,000 miles all the way there. Now, in terms of kilometers, this is 6,400 kilometers.
Exactly.
And that one is another 6,400 kilometers. Now, suppose I make a well. Suppose I drill a hole and make it go all the way to the other side.
Okay.
All right.
Chinese.
And then you take an object and assume there's no air resistance and assume there's no temperature factors. It is just a well that is completely evacuated. Okay? If you take an object and drop it from here, what is the acceleration of that object when you drop it here?
Negative.
That way, and it is 9.81, right?
Yes.
So what is the what will happen? Because of this, it's going to speed up. It's going to speed up, but the acceleration starts slowing down because it is coming closer and closer to center. When it is at the center, what's the acceleration?
0.
Zero. Because you're surrounded by matter all around, so there is no force. So you're at the center of the Earth, which means that absolutely there is no attraction from net attraction 0. So there's no acceleration here, but you have a tremendous speed. You have a tremendous speed. So what will happen? Because of the tremendous speed and the momentum that you have, you keep going. And what will happen as you go like this? Which way is the acceleration when you're here? Towards the center. And the acceleration keeps increasing as you go. And what's the acceleration here?
9.8.
9.81.
That's the infinite energy.
You see that?
No.
Now so what will happen as soon as the object goes to the other end? It stops,
Right where you jump.
turns back, and goes again.
You're gonna be
Stops, turns back, and goes again. Is that simple harmonic?
Yeah.
Yeah.
$20.
Well,
That is
now I know
simple.
never to dive into muscle like covers the entire planet.
Wow. You didn't know
Thanks,
that
Walker.
You would never be able to get out.
Alright, so that's why I said there are physical,
Physical.
the physical factors such as temperature or air resistance and all that are completely taken out of this particular example. But if you kind of evacuate something like this, and if you can manage to produce a hole going all the way and you drop something here, it should be able to go to the other side, stop, and then come back. Or if you jump into it, you just go all the way to the other side, say hi to Chinese people, and come back again.
Would it take a while, or would it go pretty?
Let's find out. Let's find out how long it takes and all that. So what is this? What is this acceleration? Is it the maximum acceleration?
Yes.
All right, so you go there. Maximum acceleration is r omega squared. Is that right?
Yeah.
And you know the maximum acceleration is 9.8. So you know this part. 9.81 is equal to r. What is r? The amplitude. 6,400 kilometers. You have to convert it to meters. So convert it to meters. 6,400 kilometers. Change to meters.
640.
And then we have omega squared. So can you find out the omega? First find the omega. Find the omega. So 9.81 meters per second square, and this is in meters, and so you'll get your omega in radians per second. That's your angular frequency. So what's your omega? Calculate. How much?
It says 0.001.
Yeah, tell me in scientific notations. Put it in scientific notations so you don't miss anything.
1.24 times 10 to the negative
10 power negative
3.
3 radians per second. And you know omega is 2 pi over capital T. Can you find out T then?
Yes.
You'll find out the time period. Find out time period. So you got this. Now keep the same number without any adjustments. Don't take it as just 1.24. Like keep the original number. It's better.
5,074.99.
5,075 seconds. And that's a time period. What's time period by definition? Time taken for? That means if I drop something from here, how long does it take to go here and come back? That is that.
4 minutes. Now and a half.
Imagine
How many minutes?
84
Hour and a half.
minutes.
84.
58.
So how many seconds? How many hours and how many? So how many minutes? Tell me in minutes.
84
85.
minutes.
80.
84 minutes. 84 and a half minutes.
So 84.5 minutes it takes for it to go and come back. So what about just going alone? So how much is the time taken to go alone? 42.25 minutes. You know, you have an idea now. So how long will it take for you to go from here to China?
That's good travel time.
You can't go faster than that, right?
That's
Yeah, so if you can actually kind of design something, evacuate a thing, and you get into a capsule, and then you get inside the capsule and you're able to go. Now it's all if you can do all that stuff. Then it'll take only 42 minutes and you're reaching the other side, and then stop the capsule there, get out from there.
Right, but if we could do all that, we might as well just like use single stage orbit and then come down.
Oh, that'll take a long time.
Yeah, that'll take more than 42 minutes.
And because orbiting is not going to, orbiting is basically like, you're going to fly.
You don't do an elliptical orbit, you just use the curve and then accelerate downward.
Yeah, but still, the time it takes for you to kind of go to a certain height and keep moving, you have to move. It's not
The fastest way between 2 points
This
is
will
a
be
straight
the fastest
line.
way you can transport something. Yes.
Let's say there is a gym at the center of the Earth. Would you be able to like float around in it?
A gem.
Why a gym?
Gym.
Like a
Like
gymnasium.
open
Oh,
gym.
gym.
Big.
I thought you were thinking
What did you all think?
You're talking about gym?
Like an open gym.
Oh, yeah, I mean, like you'll be just floating there. Yeah.
How was you trying to get a center there? Isn't it?
Oh yeah. Once you, if you're stopped over there for some reason, that's the end of it. You're going to climb out of that place. 6,400 kilometers. Climb. Okay. So it's like you're at the. Yes.
Do you think sometime in the future planes will fly through the earth?
No.
No, not planes, but they're already. This plan is already in existence. Not this, but not this way, but sideways like this.
Elon Musk is building.
Oh, like the hyperrail.
Well, sideways, because if you are releasing something here, gravity is acting this way, but a component of the gravity is acting that way, right?
Yeah.
And using the component of the gravity, you are going to accelerate from here, and then zero acceleration here, and then after that, slow down and stop over there.
Right, but you have to push it.
So you will be able to reach there much faster than you can imagine.
I still
going
go
from
from
like Mexico to Canada. Still,
That's way more than.
This is something that. This is something that can be a good transport system, not for humans maybe, but for packet. But again, think of this. If that distance from here to here is 4,000 miles, what do you think is the depth of this?
Like
2
Yeah, around 500 miles and all. It's not a small distance if you're looking at it. So this is a good distance from.
How are they going to get around that?
How are they going to get around the lava problem?
Ocean?
At the beginnings.
why not just do it on land?
Then you swear
You can build tunnels under the ocean.
Ocean is. Listen up. On a scale of 0 to 4,000 miles, what is the depth of the ocean?
I have no idea.
What events are we talking? Like Mariana Trench?
I mean, Mariana Trench is the largest one.
Isn't it like
Like a mile.
Yeah.
7 miles is Mariana Trench.
Yeah.
But then normal ocean will be like 2-3 miles maximum.
Bro.
Maximum 2-3 miles. So on a scale of 0 to 4,000, where is 2-3 miles? Not even the thickness of this line.
right?
The thickness of this line is too much for 2,000. I mean, for 2 miles, 3 miles.
What do you think's at the bottom of the Mariana Trench?
A dog.
Water. Yes.
How do they solve the lava problem? Because that's pretty deep, like through the crust, and then that's a tube with air surrounded by very hot.
There are practical issues there. As I said again, it's not going to be that deep. They may do from surface to surface like this, kind of going on the surface.
Yeah, they could do a bunch of like cuts, like tiny cuts, and they could have hooks.
And they won't be using purely gravity.
Right, like magnetic.
Yeah, it will be magnetically levitated, but they won't use purely gravity because what if it gets stuck there? So they need something to power up, but the powering up will be much easier.
How does like in Japan, the rail trains that have like the electricity, how does that work?
The magnetic levitation,
Yeah,
we'll do it next year.
okay. You're going to be in your mind.
If you're with me, you will learn what is magnetic levitation. You will see it right here too. Yes.
If you were at the middle of like the earth and stuff, would you be like pulled like apart though?
No.
Like what would be like the acceleration like all around?
It's basically zero acceleration because you're surrounded
It
by.
all like cancels out.
It's not like one side. Now you are purely on one side. Are you torn apart?
No.
No. Then in that case, nothing.
So would it be like 9.8 like every?
It's not
direction?
9.8. Less than that because if you're here, only
Oh,
little.
it's only like one.
It's only little of the earth on one side, so little of the earth on the other side. So it's going to be small, but it is even. So it cancels off in all directions. So at that moment. Anyway, you understand the idea? So what is it? How long does it take to go from here to here? It's only 82.25 minutes. Which is, 42.25 minutes is what it takes to go from here to here. So what it takes from here to here, to the center of the earth, is half of that. 21 minutes something, right? So 21 minutes you're going there. And then another 21 minutes you're going there. Another 21 minutes you come here. Another 21 minutes you back here. So that is simple harmonic motion. Now let's look at some other oscillations which are simple harmonic, and let's look at it more detailed. So simple pendulum. simple pendulum. Let's study in detail, and then you're going to do the lab on this one very soon, next week.
When will our labs be put in?
As soon as I'm done looking at it. So simple pendulum. So you have the bob here. It'll be soon. I'll be putting it soon because everyone has done it, and I have to just go into it. All right. So that's the simple pendulum's bob, and when you bring it to one side and release it from here, when you release the bob from there, when you release the bob at that position, how many forces are acting on the bob? When you release it from there, how many forces are acting on the bob?
Tension, gravity.
Tension and
Yeah.
gravity.
Here we go. At this position, how many forces are acting on the bob? Two forces. That's right. There is one force downward, which is mg, and the other force is this one, which is tension. Right? So you have a tension and this, that's it. Only two forces. Now, resolve this mg into two components. If this angle is theta, mg can be resolved into this component and this component. You're splitting into two components. Since this angle is theta, so what component of mg is acting this way?
MG.
Mg cosine theta is acting that way, right? And what is this component? It'll be mg sine theta. Yeah, the sequence of topics that you've done so far will kind of make it easy for you to understand these things because we've already done those concepts of resolving vectors and all those things. So that should not be taking time. So mg is resolved into two components. One is this and one is this. Is this bob moving upward because of the tension or downward because of mg cosine theta? No. So what do you know about these two? They're equal. T is equal to mg cosine theta. So they cancels off. So what is the only force left? Mg sine theta is the only force left. And which way is it directed?
Position.
To the main position. Look, it's pulling it this way. So this mg sine theta is acting which way? Towards the main position. Suppose it is on this side. Which way is it acting? So can you see the simple harmonic motion concept coming in through?
Yeah.
Good. Now, so net force is equal to mg sine theta, but it is backward towards the main position, so I'm introducing this minus sign. I'm introducing the minus sign because that net force is a restoring force, right? It's a force that brings it back. It's not a force that takes it further. So when it's swinging like that, it's a force that tries to bring it back, not letting it go that way. So this is a force that is trying to restore it, so I put a minus sign there to indicate that restoring force. So if this is the force, what's the acceleration?
MG sine theta times.
How do you find acceleration from force? F is equal to ma. So what is acceleration?
MG sine theta divided by.
Mg sine theta divided by mass. So what is it? G sine theta. G sine theta. Get it? Now that's going to be true at any position here. It's going to be always there. So the acceleration depends on the angle. It depends on the angle. Now here is where we use a small angle approximation. You can write that down. Small angle approximation. We will. This is a small angle approximation that is used in math generally, and learn it now so you can actually use it in math or in physics at a later time. And we need it right now, so I'm going to give you that. What is the small angle approximation? This is a small angle. If theta is very small, if theta is very small, sine theta is approximately equal to tan theta is approximately equal to theta in radians. That is called the small angle approximation. Sine theta is approximately equal to tan theta is approximately equal to theta in radians. Yes.
How small is very small?
We'll see it. Take your calculator.
Alright.
Take 5 degrees, for example. Now, 5 degrees is not too small an angle. Take 5 degrees. What is sine 5? Do you see it on the calculator? Then do tan 5. Are they pretty close?
Yes. Yeah.
They're pretty close to be almost the same. Now, for 5 degrees, I'm talking about 5 degrees. Now, if it is 1 degree or 2 degrees, check it out and see for yourself. Sine of 2 degrees, tan of 2 degrees, and see how much you get. It's nearly the same. Nearly. Only the last couple of digits have changed, right? But you can see the answers are very, very close. The close, now even for 10 degrees, check it out for 10 degrees, it is not greatly different. Sine of 10 and tan of 10. Very close. So the larger the angle, this thing kind of deviates off, right? So small angle approximation simply means for small angles. When you're talking about small angles, something less than 5 degrees and all that is considered a good small angle. So for small angles, sine theta is approximately equal to tan theta is equal to theta in radians. What is 5 degrees in radians?
0.872.
How do you change degrees to radians? Multiplied by pi and divide by?
180.
Do that and you'll see the same answer that you got for sine theta and tan theta. So sine theta is approximately equal to tan theta is equal to theta in radians. This is called small angle approximation. And so sometimes when you know that the angle is small, you can just cancel sine theta with the tan theta. You know what I'm saying? You can knock that out from the equation. Sine theta and tan theta goes. You get a good answer for the even after cancelling sine theta and tan only when the angle is small. So that's called small angle approximation. Now I'm going to use that here. So since acceleration is minus g sine theta, now I'm going to write it as minus g theta. I'm not using sine theta now, I'm just using just theta. But theta should be in radians. So this is the angle in radians. What is the relationship between that, the length, and this displacement, y? What is the relation between this, and this? What's not a triangle, the arc. You know, you have done it in circular motion. The arc length. This is the arc length.
This is equal to theta.
This is a radius.
L theta.
Good. So y is equal to L theta. Is that okay?
Yeah.
Like y equal to arc, I mean like arc length is equal to radius times the angle. That's exactly what it is. So what is theta? What is theta? Y over? Put that here. Now look at this equation carefully. Look at that equation carefully. Can you see the definition of simple harmonic motion right there?
It's directly proportional.
Acceleration is directly proportional to the displacement y, and these are constants. So this equation is very similar to minus omega square y. So what is omega square?
Minus G over L.
Yeah, what is omega square? Compare it.
G over L.
Omega square is G over L. And what is omega? 2 pi over capital T, right? So what is 2 pi over T? Square root of? Is that right? So what is T over 2 pi? Square root of? I'm flipping it. So what is t? 2 pi times square root of L over G. That is your equation for simple pendulum timing. This is the equation for the time period of a simple pendulum. How long does the pendulum take to swing once completely? Is this equation. How long does the pendulum take to swing once completely? That's your equation. This is assuming what? Small angles. That means when you're doing a pendulum, you are particularly told to make the oscillations small. Not more than this. I mean, a little more is okay. The more and more you do it, you're going away from that equation. Make sense? So don't do this. This is not right because according to this, your small angle approximation is not going to be working out right. So if you want that equation to be satisfied properly, the angle of oscillation should be small enough. That's why when you're doing simple pendulum experiment, you're told particularly keep the amplitude small or the angle of the swing not more than 5 degrees. Okay? Keep it low. The lower you keep it, as long as you're able to see the oscillation, that's more than enough. How long does it take to swing once completely? Depends on the what? The length of the pendulum. See, this is the length of the pendulum. And what is the other one? Gravity. Acceleration. So if I do this on the moon, how is it going to swing? Can you just think of the animation?
Could it take longer?
On the moon, G is smaller, so the time period is supposed to be? So on the moon, it's going to go like, the same pendulum is going to take more time. You get it? The other factor is what? Length, L. So if I reduce the length, you can see it is taking less time to go once completely. So the longer the pendulum, the more time it takes. Make sense? What about the mass?
Doesn't matter.
Doesn't matter. Mass is not coming in the picture at all. So it doesn't matter whether I'm keeping a heavier object or a lighter object. Normally we keep a heavier object because we don't want air resistance to take a toll on it, you know. So if I take a ping pong ball and suspend it, it'll lose its amplitude very quickly because air resistance stops it. So we normally use a heavier object so that it will sustain that oscillation for some time till you work. Okay, is that clear? So this is a very important relationship which tells you the relation between length and all that stuff. Now think of this. Our leg is a pendulum. See, it is suspended here. And your leg is swinging freely. So the frequency or the timing of your walk, how long does it take to swing your legs? So when you're walking, actually what is happening is you're letting your leg go. See, you're leaning forward, letting your leg go, and the leg swings to the next part, next part, next part. So you're actually like using a natural frequency to walk. So you can walk miles without getting tired if you just walk a casual walk like this. Let it free, let it dangle like that. Now when will you have to do a lot of work is when you go against gravity, like when you force it. When you go faster or slower. Have you done slow walking? It'll make you tired. Yeah, by the time you go 50 meters, you are tired. Really, because all the muscles are really working because you're going against gravity. You understand? Yeah. So to exercise, you do either a brisk walk or a slow motion walk. But a slow motion walk will be awkward because people will say, "What's wrong with this person?" You know.